When you hear the low rumbling hum of a kitchen kettle just before it whistles, you aren't just hearing water getting hot.
Oh, definitely not.
You're listening to millions of microscopic vapor explosions violently collapsing against a metal surface.
Yeah, it is absolute thermal chaos in there.
Right. And we walk into a room, turn the dial on a radiator,
Yeah.
and just expect this space to get warm. We treat heat as this clean binary switch.
Like it just magically happens. But beneath that surface, thermodynamics and fluid mechanics are waging a really complex, invisible combat.
Invisible combat. I love that.
It's true. It's a profound battle of physical forces, and it's mostly happening in boundary layers so thin you can barely even measure them.
Well, welcome to the deep dive. Today, we are cracking the code on how heat actually moves, how it changes phases, and how it behaves in everything from the mundane objects in your home to massive industrial power plants.
It's a massive topic.
It really is. Our mission today is to take the technical blueprints of thermal physics we have in front of us and adopt the exact problem-solving mindset of a professional engineer.
We really need to get into their heads for this.
Exactly. We're going to explore how we manipulate natural convection, condensation, and boiling just to keep modern infrastructure from literally melting down.
And it really is always trying to melt down.
Okay, let's unpack this. Before we get into massive steam condensers, let's stay with that kitchen kettle or that domestic radiator.
Start small, yeah.
Right, because you aren't physically pumping water or air around to heat the space. So what is the actual engine driving that heat transfer?
That engine is natural convection, and it operates entirely on localized density differences.
Density differences.
Yeah. When you heat a fluid, whether it's the water in that kettle or the air touching the metal of your radiator, its molecules gain energy and spread apart.
So the fluid expands.
Exactly. The fluid expands. And because it expands, a specific volume of that hot fluid now weighs less than an equal volume of the cooler fluid surrounding it.
Oh, so it becomes buoyant.
You got it. It becomes buoyant. The heavy, cold fluid falls due to gravity, physically wedging itself underneath the hot fluid, and that forces that less dense fluid upward.
So the cold fluid is basically bullying the hot fluid out of the way.
That is an excellent way to visualize it, honestly. That gravity-driven displacement creates a continuous circulation loop.
But an engineer can't simply build a system based on the idea that fluids push each other around, right?
No, absolutely not. They have to rigorously quantify the force of that circulation. And to do that, they have to calculate the Grashof number.
The Grashof number. Looking at the thermal models in our sources, this isn't just a basic temperature reading.
Far from it.
Yeah, it requires pulling together a very specific set of physical properties, right?
Yeah.
Like the fluid's coefficient of thermal expansion, the physical force of gravity, a characteristic dimension like the height of the radiator.
The temperature difference between the hot metal wall and the bulk of the fluid.
Right, plus the fluid's density and its viscosity. That is a lot of math for a radiator.
It is, because the Grashof number isn't just a static measurement. It's a mathematical ratio representing a physical war.
A physical war.
Yeah, it calculates the exact ratio between the buoyancy forces pushing the fluid up and the viscous forces, so the internal molecular friction, trying to drag it down and stop it from moving.
Oh, wow.
Think of trying to circulate hot syrup versus hot water. The viscosity fights the convection.
Okay, that makes perfect sense. And once you map out that battle with the Grashof number, you have to multiply it by the Prandtl number.
Exactly.
And the product of those two forces dictates the flow regime of the fluid. It tells you whether your fluid is in laminar flow, moving in the neat parallel sheets, or if it is broken down into turbulent flow, swirling chaotically.
Which completely changes how heat transfers.
But I want to push back on how we calculate this.
Okay, go for it.
If natural convection relies on the hot fluid rising and creating this large-scale circulation loop around the whole room or the whole kettle, why do the engineering blueprints insist that all these properties, the density, the viscosity, must be evaluated at the film temperature rather than the overall bulk temperature of the liquid?
Ah, the film temperature.
Yeah. Why are we ignoring the vast majority of the fluid? It's like evaluating a hot air balloon by only looking at the fabric.
That's a great analogy, but the reason is that the vast majority of the fluid isn't where the energy exchange occurs.
It's not.
No. The buoyancy effects, that extreme temperature differential, is at its absolute most intense in a micro-thin layer of fluid physically touching the heated metal.
Right.
That boundary layer is the film.
So all the math has to be hyper-focused on a fraction of a millimeter of fluid.
Precisely. In engineering, accuracy depends entirely on analyzing the physics exactly where the action happens.
Huh.
If you calculate the viscosity of the water using the, say, 50-degree average temperature of the whole kettle, your mathematical correlation will completely fail.
Because it's not 50 degrees near the metal.
Exactly. The water sitting tight against that 100-degree heating element is far less viscous. It's behaving entirely differently than the water, even an inch away.
That perfectly sets up our next massive conceptual leap.
Where we're going.
Well, if understanding heat transfer requires obsessing over the boundary layer, where a fluid hits a hot metal wall, the inverse must also be true.
Oh, yes.
We have to look at what happens when a hot gas violently collides with a cold boundary. We're scaling up from the domestic radiator to an industrial steam condenser.
This is where it gets intense.
We are talking about condensation, or essentially the sweat of the machine.
The sweat of the machine, I like that. Condensation is phase change driven by that cold boundary layer.
Right.
It occurs when a vapor contacts a surface dropping below its saturation temperature, which is its dew point.
Okay.
The vapor loses its latent heat to the cold metal and physically collapses back into a liquid state.
But the blueprints show that this phase change happens in two radically different ways depending on the surface physics. You've got film condensation and dropwise condensation.
Right, the two major mechanisms.
Film condensation is what happens when your bathroom mirror fogs up during a shower. A continuous, unbroken sheet of water forms and constantly drains down the glass under its own weight.
And then there's dropwise.
Yeah, dropwise condensation is closer to rain hitting a freshly waxed sports car. The water refuses to form a sheet. It forms distinct, isolated beads that zip down the surface at high velocity.
And from an industrial efficiency standpoint, dropwise condensation is vastly superior. It yields a significantly higher heat transfer coefficient.
Because that continuous sheet of water in film condensation is actually acting as a thermal blanket.
Exactly. Water is a terrible conductor compared to metal.
Right. With dropwise condensation, the sweeping beads of water constantly expose bare metal, meaning the incoming steam maintains direct, naked contact with the cold surface.
Naked contact is what you want.
But in film condensation, the hot vapor has to try and push its heat through a flowing wall of water just to reach the metal.
Which forces engineers to obsess over the physical geometry of their condensers. If water acts as an insulator, how do you get it off the metal as fast as possible?
So, geometry is everything.
It really is. If you design a condenser using massive vertical plates, gravity pulls the liquid down, but as it falls, it accumulates.
Oh, like a waterfall getting thicker at the bottom.
Exactly. The film gets thicker and thicker toward the bottom of the plate, and that deep layer of liquid creates massive heat transfer resistance.
Oh, which is why horizontal tube bundles are so common in large systems.
Yes.
A horizontal cylinder forces the condensed liquid to travel a very short distance around the curve of the pipe before it trips off. It sheds the insulating blanket before it can build up any real thickness.
It manages the accumulation perfectly.
Yeah.
But liquid accumulation is only one of the saboteurs engineers have to fight.
Saboteurs.
Yeah, another major threat is superheat.
Superheat, right.
If the incoming vapor is highly superheated, meaning its temperature is far above its actual condensation point, the system first has to strip away all that sensible heat before a single drop of liquid forms.
So sit cooling gas at first.
Exactly. During that entire cooling period, the cold wall is just interacting with a gaseous film.
And gases are terrible thermal conductors. So the condenser is basically operating at rock bottom efficiency until the vapor finally cools enough to condense.
You got it.
And speaking of terrible conductors, the thermal models highlight a third saboteur, non-condensable gases,
Oh, those are a nightmare.
like ambient air
Yeah.
getting trapped inside a steam pipe. Air won't condense at those temperatures.
No, it won't.
It just builds up and physically blankets the cold surface, completely blocking the steam from making contact. You have to literally build mechanical venting systems just to bleed the trapped air out of the condenser.
What's fascinating here is how the math reflects the physical reality of that liquid blanket.
Oh, so?
When engineers calculate the heat transfer coefficient for a condensing system, they completely ignore the thermal properties of the vapor.
Wait, really? Even though steam is the fluid entering the machine?
Even though steam is entering, the rate of heat transfer is entirely governed by convection traveling through that falling film of condensed water.
Wow.
The calculation relies exclusively on the thermal conductivity, viscosity, and density of the liquid phase, evaluated right at that boundary film temperature.
It all comes back to the boundary layer.
Every single time.
So we've extracted heat by collapsing vapor into liquid on a cold surface. Let's push the energy the other way. We are looking at hot surfaces boiling liquid.
The fun stuff.
And this is not just about bringing a pot of water to a rolling boil for pasta. We are mapping the exact life cycle of a bubble, because understanding how those bubbles form dictates the survival of massive thermal infrastructure.
Boiling is entirely dictated by the delta T.
The delta.
Yeah, the temperature difference between the hot metal surface and the saturation temperature of the fluid. As you increase that surface temperature, you force the fluid through three distinct mechanisms of boiling.
Let's trace that delta T. If your metal surface is barely hotter than the fluid's boiling point, say a delta T of just 0 to 2 degrees Celsius, you are in the natural convection boiling regime.
Right.
It's incredibly anticlimactic. You are technically boiling, but there are no bubbles.
None at all.
The thin film of liquid touching the metal superheats slightly, becomes buoyant, and circulates upward, transferring heat through basic fluid motion.
But as you increase the heat, pushing the delta T to roughly 2 to 40 degrees Celsius, you cross a threshold into nucleate boiling.
Nucleate boiling.
And this is the exact mechanism engineers target for maximum efficiency. Microscopic imperfections, like tiny scratches and pits on the metal surface, act as nucleation sites.
So the metal isn't perfectly smooth.
Never. Vapor bubbles rapidly form in these microscopic canyons.
They form, they inflate, they pinch off, and they rise. And this is the magic of nucleate boiling.
It really is.
As thousands of these bubbles rapidly detach and rush to the surface, they act like tiny mechanical agitators.
Yeah.
They are violently stirring the fluid, dragging cold water down to the hot surface and pulling hot water away. The heat transfer coefficient goes through the roof because of this chaotic mixing.
But that efficiency has a hard limit.
Right.
If you keep pushing the surface temperature higher, driving that delta T past 40 degrees Celsius, you trigger a catastrophic shift into the third regime.
And that's stable film boiling.
Yes, stable film boiling. The surface is so incredibly hot that bubbles form too fast, they don't have time to inflate and pinch off.
So they just pile up.
They instantly merge and coalesce directly on the metal.
Here's where it gets really interesting. All those independent bubbles fuse into a single, unbroken blanket of vapor, physically separating the liquid from the heat source.
A vapor blanket.
Yeah. It's like trying to boil water by placing a layer of bubble wrap between the water and the stove. Or like wearing a winter coat in a sauna. But wait, if you're continuously feeding more energy into the system, making the metal hotter and hotter past 40 degrees, why does the system's ability to transfer heat completely crash?
Because of the massive difference in thermal conductivity between liquids and gases.
Okay.
Water conducts heat quite well. Steam does not. The moment that continuous vapor film forms, it acts as a highly effective thermal insulator. The heat transfer rate plummets instantly.
The heat is literally trapped in the metal.
Exactly. And in a chemical refinery or a nuclear reactor, trapped heat is a worst-case scenario.
I can imagine.
The metal surface temperature will skyrocket exponentially because it cannot shed its thermal load into the fluid. The temperature will continue to climb until it reaches such extreme levels that thermal radiation finally becomes powerful enough to shoot heat across the vapor blanket.
Wow.
But long before radiation stabilizes the system, your steel pipes or reactor fuel rods might simply melt.
So professional engineers are essentially walking a thermal tightrope.
A very dangerous one.
They want to operate at the absolute peak of nucleate boiling to get that incredible mixing efficiency. But they are terrified of pushing the delta T just a few degrees too high and triggering a catastrophic film boiling meltdown.
It requires immense precision. You have to know exactly how much heat is moving through the walls of your heat exchanger.
Which brings us to the most brutal mathematical reality of thermal engineering. We know how convection works, we know how condensation and boiling behave.
Right.
But to calculate how much heat is actually moving from a hot fluid through a metal wall and into a cold fluid, you need to use those complex convective correlations we discussed earlier.
The ones that use the Grashof and Prandtl number.
Exactly. And those correlations require you to evaluate the fluid properties at the exact film temperature on the wall.
Which requires you to know the exact temperature of the wall itself.
But if you're doing a steady-state design analysis, sitting at a desk designing a power plant that hasn't been built yet. You have no idea what that wall temperature is going to be.
Not at all.
It is the ultimate engineering paradox. You need the wall temperature to calculate the heat transfer rate, but you need the heat transfer rate to figure out what temperature the wall will stabilize at.
You cannot solve it with a single equation. You have to use an iterative solution.
An iterative solution.
It is a highly disciplined, sequential process of mathematical trial and error based on the laws of energy conservation.
The blueprints lay out a rigorous 6-step loop for this. Step 1.
You guess.
Yep.
You just guess.
You make a highly educated assumption about what the wall temperature might be.
And then step 2. You use that guess temperature to calculate your film temperatures, look up your physical fluid properties, and run your correlations to find your convective heat transfer coefficients for both the hot side and the cold side of the wall.
Okay, then step 3. You calculate the total heat transfer rate, represented by Q, moving from the hot fluid into the metal wall.
Exactly. Step 4. You calculate the Q moving from the metal wall into the cold fluid.
Step 5. The moment of truth. You compare the two Q values.
This is where you hold your breath.
If the heat entering the wall perfectly matches the heat leaving the wall, your system is in steady-state equilibrium. Energy is balanced. It means your initial blind guess for the wall temperature was miraculously correct, and you can finalize your design.
But step 6 is the reality for most engineers on their first attempt.
Let me guess, they don't match.
If those Q values do not match, your energy balance is broken. Your guess was wrong. You must assume a new wall temperature, loop all the way back to step 2, recalculate every physical property, and run the correlations again.
So what does this all mean? We just guess until the math works. It sounds incredibly tedious, like throwing darts at a board while blindfolded.
This raises an important question about how we visualize thermal equilibrium. It's not blind dart throwing. Think of it like trying to balance a massive physical scale, but with a trick.
What's the trick?
Every time you add or remove a weight to balance it, the physical length of the scale's arms changes.
Oh, that's brutal.
You are hunting for a moving target. The heat entering must equal the heat leaving. The structural integrity of multi-million-dollar industrial systems relies entirely on nailing this exact iterative balance.
But because this entire process is built on a foundation of assumed temperatures, mathematical errors are inevitable.
Very inevitable.
When a complex thermal model refuses to balance, when the iterative loop completely falls apart, how does an engineer troubleshoot the labyrinth?
This is where the gap between a junior engineer and a senior engineer becomes blatantly obvious.
How so?
Well, a junior engineer will look at a failed convergence, see that the heat rates don't match, and immediately just guess a completely random new wall temperature, hoping the math magically fixes itself.
So they treat the symptom, not the disease.
Precisely. A senior engineer stops the loop entirely and interrogates the physical assumptions.
They look at the properties.
Yeah, the most devastating errors happen during the selection of fluid properties. If an engineer gets lazy and evaluates the fluid's thermal conductivity at the bulk temperature instead of calculating the precise film temperature, the convective correlation will spit out garbage data.
And the scale will never balance.
Yeah, never.
And the flow regimes are an even bigger trap. Let's say you calculate your Grashof and Prandtl numbers, and you make a slight math error.
Oh, no.
You assume the fluid is in slow, layered laminar flow, but in reality, the fluid boundary is in chaotic, turbulent flow.
That is a fatal calculation error. Laminar heat transfer equations assume heat is moving through neat, parallel layers of fluid, which is a very slow, conduction-like process.
But turbulent is fast.
Turbulent flow involves violent mixing, which transfers heat exponentially faster. If you apply a laminar correlation to a turbulent reality, you will vastly underestimate the heat transfer rate. Your Q values won't just be slightly off, they will wildly diverge. With every new guess you make, the math will push your required wall temperature further and further into impossible extremes.
So troubleshooting isn't just picking a better number. It is a forensic audit of your physics.
That's a great way to put it.
You verify your film temperatures, you recalculate your flow regimes, and when you do guess a new temperature, you do it logically. If your calculation shows more heat entering the wall than leaving it, you know your assumed temperature was too low to push the energy out. You adjust the temperature upward proportionally, letting the physics guide the iteration.
If we connect this to the bigger picture, mastering this iterative troubleshooting is not an academic exercise.
It has real-world consequences.
Massive ones. If an engineer accepts a poorly converged loop and forces a design through, they will build a heat exchanger with the wrong surface area.
Which means it won't work right.
Best case scenario, an industrial steam condenser completely underperforms, bottlenecking a power plant. Worst case scenario, the system geometry pushes the fluid into stable film boiling when it wasn't designed to handle it, the internal metal structures overheat, and you suffer a catastrophic systemic failure.
The forces are invisible, but the stakes are incredibly physical. So let's trace the arc of what we've uncovered today.
We've covered a lot of ground.
We really have. We started by revealing the hidden engine of natural convection, where microscopic density differences in gravitational displacement create the circulation heating your living room.
That invisible bullying.
Right. We explored the condenser's battleground, where dropwise condensation fights to maintain bare metal efficiency, while film condensation tries to smother the system in an insulating blanket of liquid.
We analyze the razor's edge of boiling mechanisms, learning how nucleate boiling provides the chaotic stirring required for massive industrial heat transfer.
And why crossing the threshold into film boiling creates a highly dangerous thermal barricade. And it all culminated in the complex, iterative mathematics of steady-state design. The rigorous balancing scale logic that engineers use to predict temperatures and safely build the infrastructure that powers our world.
The six-step loop.
The next time you listen to that kettle rumble, or you drive past a chemical plant and see those massive steel cooling towers venting into the sky, I want you to remember the thermal combat happening inside. You are witnessing precise, iteratively balanced energy equations playing out in real time across millions of microscopic boundary layers.
It pulls back the curtain on how heavily engineered our reality actually
It
is.
totally shifts your perspective.
Yeah.
But I want to leave you with one final provocative thought to mull over.
Okay, let's hear it.
We've established that this entire iterative balancing act, the foundation of thermal engineering, relies exclusively on knowing the precise physical properties of the fluids you are using, the density of water, the viscosity of ammonia, the thermal expansion of steam.
Which we have vast tables of data for.
Yeah, right. But we are entering a new era. The tech world is rapidly transitioning to totally synthetic, heavily guarded proprietary cooling fluids to manage the extreme heat of quantum supercomputers and next-generation batteries.
Ah, I see where you're going with this.
If a thermal engineer is tasked with keeping a vital system from melting down, using a fluid whose molecular secrets and thermal properties are literally unknown, how do they even make that first mathematical guess?
That is the frontier where established theory collides with pure experimentation.
It is a massive thermal puzzle for the next generation to solve. And it brings us right back to the beginning, looking at a simple radiator on a cold morning. We expect heat to be straightforward, we expect it to just work, but beneath the metal surface, the invisible combat never stops.